Test 1 2. Test 1 2. I'm just going to wait for confirmation for the stream, and then we can go. Okay, we are live. Turn down the radio. Soma FM. Oh.
Testing.
Just do a mic test.
Testing. Testing. Testing.
Yes. Nice. Go again.
Testing. Testing.
People are saying loud and clear, so.
Okay.
Take it away, Neil.
Good evening, everyone. My name is Neil Pandya, and I would like to welcome you all to the 4th Cyberspectrum Meetup. This event serves as a forum for the exchange of knowledge related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event tonight is being sponsored by Edis Research and is being hosted by Noisebridge, a nonprofit hackerspace for technical creative projects. Our first speaker tonight will be Jesus Molina, who will give a presentation titled War Driving in the Age of the Internet of Things with SDR. He will discuss how to discover and map radio devices with SDR, and he will present a new concept called war watching, which refers to watching IoT devices in real time, a kind of war driving for any frequency range. Our second speaker will be Julian Arnold, who is the Perpetual Intern of the Month at Edis Research. He will give an in-depth presentation about building a Doppler radar with Cantennas and SDR, as well as a short video. Our third speaker will be Yves Cox, who will join us live from Belgium. We thank him for waking up before sunrise to be with us. He will give a presentation about multi-PSK and how to use it to analyze all manner of interesting signals, such as the Aircraft Communications Addressing and Reporting System, more commonly known as ACARS, as well as weather facts, slow scan television, or SSTV, differential GPS, and more. All meeting presentations will be recorded and posted online, as well as streamed live on YouTube. The previous 3 events have already been posted in full HD video. We have set up a channel on IRC called #Cyberspectrum on Freenode as a way for remote people watching the live stream to contact the group here at Noisebridge with comments or questions. Future meetup locations will alternate every month between Edis Research in Santa Clara and here in San Francisco. The next meetup will be on Wednesday, March 18, in Santa Clara. A list of speakers and presentations will be posted about a week prior to the event. If you have any ideas about topics for future talks and presentations, then please let us know. Thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Noisebridge for providing this space and hosting the meetup here tonight. We would ask that you leave a small donation in the donation bucket by the entrance to help support them. Free pizza and beer and soda are available in the middle of the room on the table. courtesy of Edis Research, so please help yourself. Without further delay, let's get started. Balint will make a few additional announcements and then introduce our first speaker.
Thank you, Neil. Good evening, everyone. Welcome to those that have joined us here tonight, and as well to those that have joined us live online. Hope you are good. And really, I don't need to make any additional announcements because Neil does such an incredible job every time. Thanks, Neil. But at least I do have some interesting photos to show people. So just to recap, remember, hopefully you can read that out there in the internet land. Let me know on IRC. The channel is #CyberSpectrum. Thank you to these fine folk for sponsoring us and having us tonight. As always, we would love to hear what kind of talk you would like to present here, so please get in touch and either submit a talk or just even a rough idea that you've been thinking about that you'd like to get some feedback about. And even if there's a particular topic of interest, for example, tonight we'll be hearing about multi-PSK. A number of people actually commented on the discussion page that this was a topic of interest, and so we managed to luckily find somebody, or they volunteered after hearing about that. Again, after the meetup, you can head to the meetup page and look at the pages there and the meetup links. That's where we tried to post the links to content, slides, the final edited video, and so on. Next month, the next meetup will actually be in 3 weeks on, I believe it's the 18th. So keep in mind this URL, and you can also check on Twitter for updates. That one will be back down in the South Bay. Tonight we have a great lineup, and this is in no particular order, but we have our wonderful friend joining us from Belgium. So let's actually hope that he wakes up. I would imagine his alarm will be going off sometime shortly, but he'll be on at 5:45 a.m.
His time.
His time, right. So EF Cox will be going through some demonstrations of multi-PSK, and he's actually going to try and receive some signals live. He said he's got some backup recordings, but he's going to try and do it all live for us via Google Hangouts and Skype. So that'll be a first for us, and fingers crossed. We have Jesus, who is right here. He's going to kick off tonight's talk. I stole that one from your Twitter page, but it's a pretty cool picture. And as always, the titles on here are their Twitter handles if you want to follow them. They're also listed on the meetup page as well. And then, goes without saying, we have the Broadcraft, and our excellent Perpetual Intern of the Month has been upgraded to a proper full presentation slot. So we're very, very eager to hear what kind of exciting work he's been doing with these cans right here. So without further ado, I will hand it over to our very first speaker. Thank you very much.
All right, hi everyone. I'm Jesus. How's everything doing? How's everybody going? Let's start this. It's so heavy here. Okay. So we're driving in the age of the Internet of Things with Open Radio. That's my handle, Verified and Trust. That's my email address. So if you want to send me any love letters, anything you want, that's the place. No me ames means don't love me in Spanish. So we're driving, as you know, it's just searching for Wi-Fi wireless. How many of you have done while driving in your lifetime? So like 1, 2, 3, 4, 5, 6, 7. So why did we do that? It's just like the reason to do that it was just because it was fun. You go around the block and you check out how Wi-Fi's, what kind of SIDs names they have, right? We create these heat maps of how fast, how far away these things will go. And that was that time, right? So I will discuss a little bit how to do that, but now with software-defined radio, a little bit in the future, what kind of things we can see now, and what kind of fun things we can do with that. I am a security consultant based in San Francisco. Right now I'm consulting for a couple of companies. I'm consulting, and that's what my
Line you so at least our audience can see.
So I am consulting for this company about augmented reality, which is called ArcCortex. They work in augmented reality projects, a little bit novel augmented reality projects. I'm also working for the Industrial Internet Consortium, so on security, on how to secure the industrial internet and the Internet of Things in general. And you can see me like follow me at Verified and Trust in my company. So let's start with software-defined radio and security. I will give you a brief introduction of where are we and how this works. Then I will talk about hacking the Internet of Things. You know, like I will review different guys that have hacked things, such as Kim or me or others that we have, hacked into devices. And we'll talk about augmented reality. And finally, I will talk about how these two things merge and what will be the future of software-defined radios. For me, it's visualizing radios easy, right? To be able to interact with anything you have around you, not by using your computer or being logged in, but just by looking at it. You look at it, and then you will know what frequency is in, and start talking. So, security and software-defined radio. So this is taken from a website of superpowers, right? So one of the superpowers is radio frequency detection, right? And if you have followed, like if you have followed Marvel or Spider-Man with the websites, he was able to hear his, he would put some spider in you, and he was able to hear the spider and follow you around, right? And when I was reading this comic book, I always thought, how does that, right? What is like sending this. Yeah. Okay. So I always was thinking, I feel like a rock star now. All right. Okay. So I was always thinking, how this thing works. Sorry. Hello. 1, 2, 3. 1, 2, 3. Okay. Testing. Hello. Software-defined radio. Yes. Okay. So I was always thinking how this actually works in practice, right? How does this guy listens to this thing that he puts in his back? How this frequency is detected or whatever. And obviously, I never got the thing, but. Think about it, right? How cool it would be if somehow you, without any kind of device around you, just with your senses, were able to detect radio waves and connect with them, just talk with them. So, security and radio signals. So, let's go back a little bit and see what things you can do with radio signals, right? When you have a device that does something with radio waves, what are the actions you can do with it? You can discover it, know what frequency it is, what kind of modulation does it use, what kind of encoding does it use, so you can perform discovery. You can listen to it, you can listen to what he actually is sending. Once you discover it, you can actually listen to it. You can communicate with it. If you have the right protocol and the device allows you to communicate with it, you can send it to do something. Hey, yes, toaster, toast me something for me, right? That's doable, right? And positioning, that's another thing that is not discussed that much in these venues, but positioning is a very important problem right now because augmented reality, virtual reality is positioning things in a specific part of the space. And when you see a radio signal, it comes from somewhere. There's a way to find it. You can move around and find the power source and see how we can find it. That's what we used to do when we were trash. We tried to position it by looking at the power that he was providing and say, "Hey, go, you can find this thing." Now, that's what we did in the past, right? So what we did in the past is we required basically a specific hardware to discover these wireless devices. If you want to talk with a Wi-Fi access point, you need a Wi-Fi receiver. There was no other way you can do these things. The software-defined radios were really expensive, so you cannot really do that except if you were in university. So you just have to buy this device and listen to the frequency. The one that everybody loved is Wi-Fi because it was everywhere. There's all these access points. So you used to do this tool called Kismet, and that still exists. And actually, for this project, I happen to use it. And one of my points is that I cannot understand how I'm still using this thing that this code that was 15 years ago is still there, right? So after we use this Kismet thing, we'll have the GPS points that we have seen. That in every GPS point we have went, and then we'll do these heat maps. So what happens right now, right? You don't really need to have a specific hardware to listen to frequencies. You can use software-defined radio like HackerRef or Etus devices or USRPs to listen to any frequency and to create software to communicate with it. In general, as long as you have the profile for this device, you could be able to listen and to communicate with any device. As long as you have encryption, if it's encrypted, everything else you could do. It's not couldn't be done right now just because it's very cumbersome. I'll discuss that, but you could do that. Now, the discovery of these devices is still done by hand. I will discuss also how this is done more or less. But when you see a new device and you don't know where it is, it's not that you can just go to the cloud or something and ask, hey, what is this device? What is these frequencies I'm seeing? What is this thing I'm seeing here? And send it to there. You cannot do that. You have to do it by hand. You can just say, oh, this is looks like AM, looks FM, looks like OK. So you have to do it by hand. Listening, after you have made the discovery, listening is actually not that difficult. You just use SDR or hardware, and I will discuss that a little bit later, and communicating the same. You can use SDR or hardware. If you know what hardware it is, what kind of frequency, what kind of encoding, you can use hardware that talks that, and you don't have to code it. Positioning, the same thing. Positioning is something that you don't have any kind of way to know where things are, really, when they are communicating with you. You never had, and until now, there was not the need. You were talking with this toaster, that's fine. But in the Internet of Things, it's going to change. When you talk with the toaster, you want to kind of see where the toaster is, or you actually are communicating with the toaster and not with the TV, right? So if you don't have something here or a remote control, and you just have a headset or some augmented reality in front of you, what you want to know is that who are you communicating with? You need to have some kind of form appearing or some kind of augmented reality way of talking with this device. So let's discuss a little bit of what, now, moving to security, right? What happened, I will talk about three things that, happened in the IoT about security and how was it done, so you understand a little bit where I'm coming from. So one of the things is that, this is all getting for wired, except one. So the first one is hackers can mess with traffic lights to jam roads and resource cards. This is an article that appeared in Wired, and this was an actual talk in Black Hat, right? By Rudolph from IOActive. And so the question is how this guy did it, So Cesar Terrudo, what he did is basically so that in every road there was these little bumps in the road, right? Little bumps in the road. And he thought, well, that must be because something buried in the road. And he was right. So he started doing some research, and he discovered that in the roads there is sensors, buried in the road. And these sensors are done to evaluate if there is traffic jams, how many traffic is coming through. So he decided he was able to evaluate the security of the sensors. Now, what he could have done is use software-defined radio to check the frequencies, and do that stuff, But as it turns out, it's kind of complicated. There is no way for discovery these things were buried in the road. So what he did is call the company. So call the company and say, hey, what are you guys using for this, Can I buy it? So by social engineering, he was able to buy it, actually. So he got the sensors, he got the access point, and he started to review the firmware and the access point, and he was able to hack it. He saw that there was no cryptography, the firmware was not signed, so he can change the access point. He can fake that he was sensors. But the point here is that he could have done it using software-defined radio. He did it this way because it's just easier, right? The second is plugging for myself. so this is here's how easy it could be for hackers to control your hotel room. That's a talk I did in Black Hat and an article that appeared in Wired too. I was in a hotel in China, and I was able to hack all the rooms. So I was able to switch on the TV in room 300. I was able to change the thermostat in room 350. I was able to switch on the TV in room 400, right? So this is kind of scary, that like somebody like me is able to control every room in a hotel, right? Every room. So how I did it, these guys, for each device, they use, for each room, they use an iPad that was able to control the room. So with the iPad, you can control the thermostat, the TV. So it turns out every device uses an internal protocol called KNX. And some of these protocols actually use radio frequency. But I didn't use that. Again, I could have used software-defined radio to find all these devices and see how to connect with them. Instead, what they did is that in order to talk with the iPad, the hotel used a router that used wireless. And the wireless was unprotected. So I was able to check the wireless, check what protocol they were using, reverse engineer and creating my own Python script. So there's two ways to do that. This is like what Vadim did, which is one of the pagers to inform people that they need the food, right? That didn't appear in the news, like Suha. But anyway, but the point is like he actually brute forced it. So he didn't use a router. He didn't he didn't call the pager people and say, hey, what guys, what's going on? He actually created the flow graph for that, and as you can see, the flow graph, it's for hacking these pagers, it's quite complicated. You can imagine this flow graph for things that are a bit more complex, right? I'm coming something here, don't worry. So what do you do to hack a thing? What can you do to actually hack something? What are your venues? You can get the hardware. If you know what the device is, you can just get the hardware, modify the hardware, talk with it. You can use off-the-shelf hardware, and like me, and try to use a router, and then decode what the router gives you. For example, a lot of companies right now, end-to-end companies, are selling routers for the different protocols, which basically are bridges between one wireless access points, actually, and all the other protocols. So you can actually use one of the routers. That's what I'm looking right now, I got one of these routers, and you can talk with a lot of devices, Zigbee, Bluetooth, and you can communicate with access point. So if you're able to kind of tame that device, and make it so it will follow your instructions, you can actually see all these devices. Or you can brute force, which is what I would like to do. I would like to have a way, a very simple way, to somehow communicate with devices without having to create these huge flow graphs, which I think are necessary right now. Of course, are necessary, but I think the good way to do that would be to have some kind of profiling of these devices. So this brute forcing is made a little simpler. But the important thing that Vadim has shown is that it's possible. You can get any device, but you can actually brute force it and talk with it, which is what is the future, right? You can see any device and you can talk with it. That's the important thing, and I think that's the important contribution of this. And the thing is that, as it turns out, devices are usually insecure. You find a device that is not, you cannot communicate with a router or anything, most likely this device will be insecure, because I am in the Industrial Internet Consortium. I see the devices that people put up there, and these devices basically are, well, if it operates in a frequency which nobody has access to, nobody can listen to it, so it must be secure. That is how the flow works. Things are changing slowly, but there's millions and millions of devices being deployed right now, and I would say most of them are open. And if you are able to listen to them, discover them, listen to them, communicate with them, you can do whatever you want with them. Just to give you an example, parrots. I don't know how many of you like own a parrot, one of these like drones. Nobody owns a drone. That's kind of amazing. Anyway, so like a parrot, it's an access point. You can, if you can talk with an access point, you can talk with a parrot. And obviously, if somebody is like with his parrot and he does not use encryption, which most of them don't, I've been there. You know, I've actually like the parrots. It's interesting, but that's where I'm coming from, right? Parrots can be checked right now. You can see all the parrots are in the sky, and you can hack already one of them because you can use the same methods we used to hack access points in the past. You just authenticate whoever is using the parrot, you authenticate to the parrot, and now it's your parrot. That's it. That's as easy as it is. And you can test that basically because, you know, I saw that because I was using a parrot, the battery of my phone died, and suddenly, like, I saw my friend taking it away, you know, so that's as easy as it is. But every device is like this, more or less, you know. Most devices in the Internet of Things are working this way. Now, I'm talking about brute forcing, what Barin is, like, I guess most people are understanding how do you brute force a device, you know, using software-defined radio, but I will discuss it here, so you understand what the problem is. So first, in order to understand, to force a device, you have to know what frequency are being transmitted. That's really the most difficult part, you know, when you say device, you don't really know what is talking. You know it's radiating something because you're maybe communicating with it, but you don't know what frequencies it is. Then you want to know, you know, what bandwidth is using, modulation, baud rate, so how fast is sending message, like the message. The encoding, if it is Manchester encoding or something, so you can transmit and receive, and encryption. There's a little bit more things, of course, but I'm trying to water this down so I can move forward. So learn about the device. So as interesting as it is, and I try to automate this process a little bit, you know, because I'm trying to do some cloud server that actually does that. Basically, every device, if it's radiating, it has to register with the FCC. So you can go to the cloud, go to the FCC, and like every device, if you turn around, will have a code there. If you press this code and put it there, it will provide information about this device. What frequency is radiating, more or less. It will not put the encoding, but it will put some performance charts to see how far away is encoded is emitting. So with this information, you can more or less tell what kind of encoding it has. So the first step is to go to the FCC and check, right? The second step is this, which is the most not super annoying, right? You know, you have to go to baud line or something, check, you know, what's exactly it is, and it's done by hand, right? It's like, oh, so more or less, because I've seen that before, must be OOK or AM or FM, right? So that's how things work right now. The third is to transmit, you know, or like to the code. So this transmitting phase, you can do what he did, like brute force it. And a lot of people, what they do is they use, you know, you can brute force it, create a flowchart, use HackerRed, for example. Or if you use like a protocol that is much more known, you can use something like the thing in the right, which is not a software-defined radio in particular, but has an API where you can tell it, hey, transmit in that frequency, OK, and with this baud rate, and it will transmit that. You don't have to do the flowchart. It's a prototype for you. It's a device that prototypes whatever you tell him, so you can like send some kind of signal very fast. We'll discuss that a little bit later. And positioning. Positioning is again, it's hard, you know, because GPS, and I've been experiencing that because I'm doing augmented reality now, is really imprecise. The CPS you have here, it's just, you will, you know, for you that usually people use GPS for the road. You know, you want to go to A and B, and the GPS, you don't need precision for the road, right? You know, you can be like 100 meters away and it's fine, you're driving anyway. But if you want to say, hey, this device is right there, this device is right there, GPS is unusable because it will tell you this is right there, then it's here, then you move around. So GPS is too imprecise for doing these calculations. So again, we want to discover what this device is, not more places in 100 meters radius of here. So, augmented reality, I would like put a demo video for you guys to understand a little bit. So this is actually a precision GPS here to do this augmented reality. I think it's easier. So we're driving around and we're testing our engine to do this augmented reality and we're driving, right? So we were trying to position different things in the real world to see how they will look like and what was best for us. So we were putting some coins there, right? We're moving around, like kind of collecting them. We put it like a basketball player right there, And so then positioning these things to see what was the best thing you can do that. But you understand the concept here, right? These things live in an augmented reality world, but a lot of the things we communicate with us, our devices, and we want to see where they are, and maybe they will be so small that you cannot communicate with them. But this way of doing things is easier to see what's going on around you and to communicate with it. And for security, to attack it, right? If this was access points, it's very easy to say, like, I want to attack this access point, or I want to see what this access point has. So that's what we're building right now. This engine to detect radio waves, position them, and talking with them. Let's go back to the. Okay. So what are the goals of this thing that we're building here with? So what are the goals of this thing that we're doing here? So we can overlay radio frequency communications to human visions. And with that, at the beginning, we were doing cell phone and Google Glass. That was a year and a half ago. Google Glass is not really a augmented reality device. It's like a CSI device, so we move away from that. We have cell phone. If I can, it's kind of difficult again to do demos because of the GPS. It's always like scattered around. But if not now, later I will do one. So we try to like overlay information on top of whatever exists. The information acquired, we want to have different layers. We want to like get information acquired from layer 1 if you don't have any more information, such as if it is just a radio wave, or to layer 7, which is like what exactly is being communicated. For layer 1, you will only be able to, it's like there is something radiating on this frequency. For layer 7, you will be able to see. So in the initial project, we want to relay layer 1 power information for 802.111 access points, but we actually did that and we moved to Bluetooth, and we'll discuss a little bit more about this. So this is an example of a Wi-Fi in a coffee shop, which we're actually developing. It's not finished, but we're doing this thing. So what we to provide very simple information of who is connecting with which, right, person. So already, if you use Kismet, you can see the wireless access point and the clients. That's information that we can see because they are communicating, and there is tools to the code until layer 7. You can know actually what they are communicating. You can know that, of course, there are some other using SSL, but a lot of things they do, they don't. And usually in an access point, which is shared by all these people, really there is, no security. So it's something like this, you want to see like this person is connecting to this access point, how much traffic is he using compared to this other guy. So kind of see like a little bit of the traffic everybody is using. So also you can see like what kind of Facebook they're using, Twitter, other Facebook. That's a little bit more like in a creepy level. But the truth is that you can get all this information. This is like something because you can see what Facebook is, even if it's encrypted, it doesn't matter because you can see the web page, you can see the Facebook person. So you can know what people are there in your surroundings just by looking at it using augmented reality. Now, the architecture for doing this, it was this. This looks quite beautiful, right? It's just a preprocess, a sensor, some process in the cloud, some post-process, and a receptor. That evidently didn't work as I expected because the first thing I used as a sensor was the RTL LDR, and then I used the HackerRef. But the problem I had is that the preprocessing tools doesn't exist. I cannot really pre-process whatever happens from a HackerRef easily. HackerRef and all these things are not designed to get information readily. Are designed to collect a certain number of samples, and then you do whatever you want with it. But this pre-processing things like linear radio are very just want to see things fast, like, okay, just tell me what's going on there. What kind of frequencies that exist, what kind of devices do you think they are? These kind of things doesn't exist currently. There's not easy tools to do that. The architecture in the cloud seems easy too, because if you have gone to conferences, there's a lot of M2M, machine-to-machine cloud services. Tennis has one, Ka is another service. There is like plenty of them. And I thought, well, if I collect a lot of data and push it to the cloud, somebody will help me like tell you what device is which. But that's not the truth. The truth is that these services work by providing you with a set of defined profiles of devices, or you have to bring your own. So you have to say, well, I'm using these devices, and these are the profiles of the devices. So that didn't work very well either. And for post-processing, also it's a problem because right now for augmented reality, there is not really an engine. Now we are using Unity because everybody's moving to this augmented reality thing, which is called Unity. So we started using Unity. So we dropped our previous sample. We have the previous application, but as it was very difficult to reconfigure, and a lot of people didn't support it, so we moved to Unity now. So that's what's really easy. Like the dream was great, but it didn't work. And we discussed like what we can do to make it work a little bit, right? So that's actually what I have right now. What works for me right now. I have in the sensor, I have a alpha and a Ubertooth. I have also all these HackerRefs and stuff, but still I don't know how to glue them really into the whole thing. And that's what I would like if you guys, if anybody can, you can work together on this. I'll be happy or anybody listening in your house if if you want to work on this project. Just basically harmonize this, so we don't really have to do all this network in the device itself, but we can like push this information in different layers of the software-defined radio to the process. In my architecture right now, I have Kismet, which is a beautiful tool in the past. Now it's kind of a very over-bloated software, which you need to control it using a client. So you have to like build your own client, collect the information you want from it, and then push it down. Interestingly enough, things like Ubertooth. I don't know if you're familiar with Ubertooth. So Ubertooth is it's a software-defined radio. It's a device which is specifically geared to listen to Bluetooth. Bluetooth is wide spectrum, so you cannot. It's very difficult for you to just sample a range of frequencies and get Bluetooth, because as it's such a wide spectrum, it will go out of your band. So Michael Osman and a partner decided to create this Ubertooth, which is chip. They put it together in different frequencies, and you get the results of. You can see the whole Bluetooth spectrum. So basically, you can snoop on Bluetooth. We did that because we want to see in real time all these Bluetooth devices that exist right there, here. And actually, we can. I cannot show it right now. I will get my Ubertooth, and I don't have the hook right now. But if you talk with me, I can like give you a demo on that. We can actually see all these devices, so we can see in real time if this thing, the device that exists right now. But there's a little bit of problems with that. First, Ubertooth only works with other things, but the only way to interact with it easily is with Kismet. And Ubertooth also has some problems on, it cannot receive the power. Probably it can, but it doesn't give it to Kismet. So I don't know how much power is transmitting these devices, so I cannot see how far you are from me or how close you are from me. So for augmented reality, it doesn't make much sense, right? You only see a list. So there is all these problems. In order to talk with the device, I decode all this information that Kismet provides, and I push it down using a RESTful API, which is very simple because in augmented reality, the only thing you want to know is the position, the name, and what interaction I can do with the device, right? So can I talk with the device? What kind of things I can do with it? So I can say the problems to this thing of watching in real time all these frequencies is there's no high-level libraries in radio. So if I only want to say, well, in this spectrum, what devices exist, and can you provide me information about the devices, this doesn't exist. If you know Nmap, which is the network mapper, you'll do Nmap like an IP address and provide a range of ports, and it will check all these ports to see if they are open, and then it will check what kind of server is in that port, and then it will provide some profiling to even tell you what the server, what operating system has. We need something like this for frequencies, in my opinion. We need something that you do f-rate, f-map, and say, from these range of frequencies, tell me what things are there. Give me a profile of, what things are there. So, in reality, that is not, that's possible, it's doable, but it's not there. As I said, Kismet is all and difficult to support. However, things like UberTooth is still doing plugins for Kismet, so it's what I'm using right now. Kismet is a write your own client thing, so you have to record the clients. I have that in GitHub if you want to check it out. There is no support proposition for UberTooth, and the M2M is in infancy. This is a sample of the REST API that is consumed. You only have the latitude and longitude, and the BSSID and the ASSID, and we go from there to display that. I can do that also for Bluetooth clients. It has the same pattern. It has also it doesn't have an ESSID, but it has a BSSID, and from that you can tell what kind of device it is. So you can see it and actually know that it's a cell phone, what kind of cell phone it is. So in the next 6 minutes, well, let me finish this because the demo may not work. So, so what's the future of radio security? Is we need off-the-shelf hardware and libraries to listen and communicate. We need to create some automated discovery so we can, be more on there. And what I think is very important is precise positioning and create cloud profiles for listening and communicating. So now, M2M services are already asking for profiles of devices, but the amount of information of these profile of devices is very minor. I think for software frame radio to move forward, these subgroup profiles of each device should be available. So not only you have to say this device has this information that it's going to send you, but also if you want to talk with this device, you can use this software, right? Just make of the devices. All right, then let me. This is a couple of things. This is the new augmented reality gear, and the second thing you see down there is the Microsoft glasses that they are to provide. Microsoft has said that this is the future for them, right? To provide this holographic information in front of you, rather than using a computer to provide all this information there. On March 7th, it will be a meta augmented reality glasses hackathon, and I'm going to participate to provide this and use the classes they are having to see if we can provide more information about it. Well, now I'm going to try to connect with this and give you a sample of what we have. See if that's going to work. So. Why is it not working? It's not connecting with this link.
I think we broke the Wi-Fi.
Yeah.
Oh, okay. So that's why it's not working. All right. Well, anyway, so I have the application here, so you can come and I can show you the application and I can show you how the augmented reality thing works. So that's basically it. Anyway, so that's basically it. I will go around and this right now is trying to show you the screen, the stuff, but it needs the Wi-Fi because it's connecting with by Wi-Fi with my Android phone. But if you want to see the demo, like I'll be around, just like grab me up and we're good. Thank you very much. And if you want to participate in the project, just send me an email or a Twitter or whatever. Thank you.
Is the Wi-Fi back? You might be able to try it again if you like.
Okay.
I think it's back up.
Oh, okay. Let's give this some go. All right, so this one go. Sorry about that. All right, thank you. It didn't work for me.
Thank you very much. Do we have any questions before he disappears? We'll try and get it back to do his demo once we've established the Wi-Fi is working correctly. Really get set up. Oh, you're already ready to go. I think this is the fastest turnaround we've ever had. So efficient. All right. So next up we have Julian talking about how to build your own radar using SDR, and we have the radar right here. I guess at some point you'll need some audience participation. You have to select somebody from the audience, right? Well, let's do this the question. Take it away, Julian.
So welcome everybody. Nice being here again. Yeah, today another project. Radar. So very exciting. Everybody loves radar. So when we start, we're taking a quick look at how it all started. So history. First, what radar? What does it stand for? It's radio detection and ranging. And the first one to demonstrate that radio waves can be reflected from solid objects was Heinrich German in 1886. And then the first real product, which was a ship detecting device, was patented in 1904 by Christian Hülsemeyer, also German. And then, the massive development of radar systems, like we know them nowadays, that started, of course, with the war, with World War II, and they did massive research there in a lot of countries. So that's enough for history, I guess. So let's take a look at the basics we need to know to build our radar system. So first of all, there's the obviously important radar equation. So what the radar equation tells us is how your transmitted power is related to the received power you get back from your target once your signal gets reflected. And so in detail, that means that PR is your received power. That equals your transmitted power, the gain of your transmit antenna, the gain of your receive antenna, so which are properties of your antennas, which are important, what we'll see later. Then you have your radar cross-section of your object, which you want to be as small as possible if you build stealth bombers, which is bad for our purposes. So we want a large radar cross-section, so that a lot of energy gets reflected. Then we have this F to the power of 4. F is basically modeling your environment, like your multipass and stuff like that. And then at the bottom, we have what is a port. We have this R to the power of 4, so which is your range. And so that says that your received power will decline with the force power of your range. So no matter how much power you put in your radar system, what you receive will probably be pretty small. So you better make sure to get your antennas right, to get your signal processing right, and to have a efficient as possible receiver chain. Okay, so that's the radar equation. Maybe even more important for us is the next one, which is Doppler effect. So who knows what the Doppler effect is? A lot. That is good, because I guess most of you know what fire trucks are, and if you've seen a fire truck, you know what the Doppler effect is. So if the fire truck is approaching you, you hear a high frequent noise, and once it passed you, you hear all of a sudden a low frequent noise, and that is the Doppler effect. So if a signal source, fire truck in our example, is approaching you, you as observer will frequency signal or see a higher frequency signal than the source is transmitting. That's what the first equation there is telling us. So the received frequency is your transmitted frequency multiplied by this VC, which is the velocity, the speed of light, divided by speed of light subtract the speed of your object. So now, for radar, it is a little bit different, because for radar, your source and observer are basically the same, right? Your radar device is the source, and it's also the observer. And the object is moving towards you. You get a factor of 2 in that equation. Then in the end, you get this this received frequency here, which is 2 times the speed of your object multiplied by the transmit frequency divided by the speed of light, because that's pretty boring. Oh yeah, thanks. I have an example, which we will later see in a video, so you better pay attention to that. So let's say we have a normal street, which is 25 miles per hour speed limit, which I converted for you because we all love the metric system in meters per second. So roughly 11 meters per second. And our system is operating at 2.4 gigahertz. So that results in a Doppler frequency shift of 176 hertz. So that's basically what we expect from our radar to tell us. So, but before we decide, or before we build a radar, we need to know what kind of radar we want to build, because there are different kinds of radars. So the first type, and I guess the most well-known, I would say, is the pulse radar. So the principle here is that it doesn't involve the Doppler effect, but it's still a radar. So you transmit a very short pulse of high energy, start your stopwatch, and wait for this pulse to get reflected back from your object, and basically count the time. So the problem with this approach is, especially considering software-defined radios, that you need the ability to generate very short pulses, because you want to be finished transmitting your pulse before the pulse is coming back to you, of course. And you need to be able to resolve the timing very, very, very accurately in order to tell how far the object is away from you. So that's not very practical. So let's have a look at another type of radar, which is the FM continuous wave radar. So that type of radar also allows you to measure the distance to an object, and it does that by transmitting a FM modulated continuous wave. And it's kind of hard to imagine that, but say you have this wave which is FM modulated, and if you receive that wave back, you will have a delay, of course, because of the past your signal travel. And because it's FM modulated, you will get a difference in frequency, a difference between your transmitted and the received signal, and that difference is dependent on the delay and thus on how long the path between you and the target is. So that way you can more easily, without needing to generate short pulses, distinguish the distance to target. But because it's our first system, we want it to be as simple as possible. That's why we go for an even system, which is the continuous wave radar, so without modulation. So what this system does, it just transmits a continuous wave and then uses the Doppler effect we looked at earlier to tell how fast a target is moving towards you or away from you. And it turns out that that is very easy to create using a software-defined radio. That's why I picked this system for my implementation. Now, before I go into the actual implementation details, I want to tell a little bit about where I got the inspiration from, because there's this very, very good project, the MIT Open Course project about how to build your own radar. And they had this great idea of using coffee cans as directional antennas for radar. And I thought, whoa, that is very interesting. Coffee cans, I mean, they're cheap. You can buy them everywhere. You just need to pour the coffee, make sure not to waste it. And then they have this modular RF design. And, well, while looking at that project more closely, I took a look at this RF design. And what we got here is basically an oscillator, an amplifier, a splitter, which is transmitting one part to your transmit antenna, and the other part of your signal to this mixer, which is mixing the transmitted signal with your received signal. And while looking at that, I was like, whoa, that's basically what is in every software-defined radio already built in, right? You got that in every software-defined radio. So I thought, well, I don't need that modular design. I don't need all these parts. I just take my software-defined radio. And then, because all that is inside here, everything I need are these cans, right? So that was kind of my idea. And then I started building the antennas. And I don't know if you can see the antennas. They're right here. So they exist. I did it. And I want to talk a little bit about how to build these antennas and what you have to account for. So first of all, the antennas can be used in the ISM band. So in my case, for 2.4 gigahertz. And the only thing you need to do is pour out the coffee, drill a hole inside, and put a waveguide coupler inside. Now what that is basically is an SMA connector on the one side and a wire on the other side. The wire is acting like a monopole and coupling into your can, which is basically acting as a waveguide. So that's all to the mechanics you have to do. So that's pretty easy, but you need to match your antennas. Now, what does it mean? Does everybody know what I mean by saying you need to match your antennas? That's good, yes?
No, I don't.
Oh, okay. So, yeah. What that means is basically that you need a network analyzer. And I just assume that, or I guess everybody of you has a network analyzer because they are so cheap.
How much?
Pretty cheap. I won't go into details here. And yeah, and they're pretty awesome devices, and you need them for exactly stuff like that to match your antennas. So this is my setup here. Here's my can. Here's the network analyzer, and so what we want to achieve by this matching is that all the energy we put into the antenna is being transmitted instead of being reflected back into our coaxial cable. And the network analyzer can measure exactly that. The network analyzer can measure if the network analyzer is applying a signal to the device, so the can, how much energy is getting transmitted and how much energy is getting reflected back to the network analyzer. And that is called the S11 measurement. And so let's take a look at this S11 measurement without doing anything, just connecting the antenna to the network analyzer. That looks like this. So we're looking at a plot of a frequency range from 1 to 3 gigahertz, I guess. So in the middle we have 2 to 3, here's 2.4 gigahertz. And this is this S11 parameter. So it's telling us how much energy is reflected back to the network analyzer. And we want that to be as small as possible. Now, as we see, it's close to 0 dB, dBm, which is not, what's dB? Which is not very good. So a lot of energy is getting reflected back. So our radiation is very small, which makes our antenna gain very small. And if you recall the radar equation, we need a lot of antenna gain. So we need to match the antenna. The only thing you can do is cut this small wire, this monopole inside, shorter and shorter in small chunks, and make sure you don't cut too much because it's very hard to get the chunks back into the antenna. So that's what I tried. I tried to get my hand inside the antenna and tried to cut off chunks of this wire, and then did measurements of this S11 parameter again. And so in the end, of course, I cut a little bit too much, but it turns out by bending the wire inside the can, you can also tune match your antenna. And so in the end, it all worked out. So that's the final plot. Now we see that at 2.4 gigahertz, there's very, very little amount of energy getting back to the network analyzer, so the can is not transmitting all the energy, which is exactly what we want. And we achieved that just by cutting a small wire inside the antenna, which I think is pretty amazing. So I was happy and did another measurement, which is how good do the antennas couple. So if I transmit on the one side, how well do I receive on the other side? And it turns out that that was pretty good without doing anything else. So that's called the S21 parameter, which tells you how much energy basically you're getting through your system, and you want that to be very high. So, and we see we are close to 0 dB, so that's pretty good. So our antenna system is actually working pretty good, which is surprisingly because it's just 2 cans and 2 holes. So now that system was set up, I needed to think about data processing. Now, like I said before, all the stuff we need and that the MIT guys had on this wooden board is inside a software-defined radio. So the idea was just to hook up the software-defined radio, transmit on the one antenna, receive on the other antenna, and you basically just use the laptop to display what's coming out. So you take your incoming signal and put it inside a waterfall plot, which is doing an FFT and displaying it over time to see if there is a Doppler shift involved in your signal or not. If there isn't, you will see nothing. If there is a Doppler shift, you will see it on your waterfall plot, that there is a line appearing on your waterfall plot. But the Doppler shift, like we calculated before, will be pretty small. So if you work at high sample rates, so with these devices you can't go to sample rates as low as you want, so you have to account for that in software. So to down convert to lower sample rates so that you can see this small Doppler shift clearly on your plot. And you need to make sure that you get a good compromise between frequency and time accuracy. Because what the waterfall plot is doing, it's doing an FFT, and so the more resolution you want in frequency domain, the more time samples you need to capture. But the more time samples you capture per FFT, the lower your time resolution will be. So yeah, you kind of need to find a compromise. Or if you better than just a plain waterfall plot, you can grab some of Boolean stuff, which gives you more accuracy by basically concatenating the FFTs, which is called overlap plot, I guess, right? Yeah. So that's pretty cool. So that's the flow graph. let's first look at this top part. The top part is just our user, our software-defined radio device. And as I said, we could just let it transmit, just a continuous wave. But because in software-defined radios, you have direct conversion, direct down conversion without an intermediate frequency stage. You have to deal with DC offset. That's why I did not transmit just a plain carrier, but fed in a sinusoid to get rid of these of this DC offset. So then this is a transmit side, so very simple, just a sinusoid to not be on DC. And then on the receive side, which is the pass here on the bottom, user. So this is all, so the transmitter and the receiver, this is all one device, which is this one. So, and here we have to again use this sinusoid signal to get rid of this sinusoid signal that we put in here. So in that case, the software is getting rid of the DC offset for us because we never operate at that point. So, and then what I said, we need to downsample the signal because the sampling rate in this case is 1 mega sample, and that's way too much for the small Doppler shift we want to observe. So I downsampled it to 1 kilo samples, and when you downsample, of course, you have to low pass filter, and that's what this block is doing. So is everybody still following? Okay, good. And yeah, and then it's just the display. So the waterfall display, which is doing the FFT for us and displaying it for us. So you can see that this flow graph is not very complex, especially compared to what we've seen earlier from Baldwin, this fancy flow graph. So it's really pretty simple on the software side because the software-defined radio is doing everything internally. And then if you run that, you will get something like this. See here. So this is our waterfall plot, and these are the cars in front of the National Instruments building in Santa Clara. And what we see one car here driving away from us, one car here approaching us, and there's another car driving away from us. And what we see here in this waterfall plot is the car approaching us. So that is a Doppler shift that we see there of around 300 hertz. And on this side, we see this peak is this car, and this peak is the car behind that. So you can see it's, I would say, working fairly well, and a video that's demonstrating that even better. So is that clear how the display works? Okay. Let's take a look at that video. So first we have a test driver operating at the speed that we had in the calculation before, 25 miles per hour. So we would expect a Doppler shift of 170, 180 hertz. So let's see. So there's our test driver. He's happy to take part. And there's our Cantena system. Because it's operating at 2.4, it sometimes gets confused by Wi-Fi signals. And so now he made a U-turn, and he will approach us at 25 miles per hour. So we should see 100, 200, so around here. The peak should appear around here if he's a good citizen. And
driving precisely at the speed limit.
I hope so. The equipment is not that precise. So there he's coming. And yeah, we see the peak like here, 170, it might be 180, we don't know exactly. And then you see the other cars there, of course, faster, because everybody's driving faster there. This clip shows that it's also working for pedestrians. So I got lucky and there was a runner coming by, and you see him right here. There he is, so it's working. And then there's a car, you see it here, it's of course way faster. And then you will see these people going way too fast, like him. And minute, so I should start to collect fines. Make a lot of. I guess we have one more car coming that's even faster. Yeah, there he goes. Like twice the speed limit. That should be, yeah. So that was the video. Now I try to make a live demo. So who does not want to get any more children? This person can participate in the live demo. Any volunteers? All right, we have a volunteer. We got a volunteer.
Let's take a bike.
So I have somewhere a metal plate. Here. Because radar cross section, that is a metal plate. Yeah, we'll wait till it boots up.
It works better when you see it.
Almost done? All right. So if you now wave that fast to the, so you have to approach the cans a little bit faster.
Radomes. What about your radomes?
Oh yeah, we could take off the radomes.
Oh!
So now we can approach the cans, and there you see the peak. He's coming. He's approaching the cans, and then yeah, can you see that? It's not very clear, not like a car, but you can see that it's working. It's operating. All right, thank you very much. That's it. Thanks. Any questions on building your own Cantena radar? Yes?
What causes the blip as the object crosses from approaching to going away? There's like a blip all the way across the spectrum?
Yeah, basically that is because you also get a lot of interference by this, so you not only see the Doppler shift, right? So I guess that's a big part of it. And then, like if you look at the cars, you don't aim at them. So I was kind of steering this in an angle, right? I guess that's also part of it. And then of course you have to do this FFT, which is not perfect. Yeah, it can have several reasons. I can't give one. Yes.
Yeah. Well, I wondered if you ever put together other kinds of radar. I'm interested in wall penetrating radar, so you can look at the pipes and the wires inside, other side of a wall or whatever. I mean, or look at stuff in cardboard boxes and find out what's inside the boxes without opening them. Have you ever made a high resolution? This is a fairly low resolution radar, but have you ever made high resolution radars?
So this radar is only detecting movement, right?
Yeah.
So if you want to look at targets, say behind in a box, you need another type of radar. So you need to like have this pulsed one or this modulated one that can give you distance to an object. And also, if you want to penetrate through material, you have to, you probably want to operate at different frequencies and not at 2.4 gigahertz. So but that's a totally different story. So
have you ever tried to make one?
No, I didn't.
Okay. I mean, one of those kind. I know that Concrete Scanning Systems Incorporated run between 1.6 to 2.6 gigahertz, and it's for scanning the concrete floor so you can find out where the rebar is, so when you drill a hole, you won't drill through the rebar.
Yeah, I guess these systems definitely exist, but it's definitely not as easy as implementing this movement detection Doppler radar.
Yeah, but can you implement, using SDR, implement a ground or wall penetrating radar?
I'm pretty sure you can, yeah. Depends on how much effort you put in, but I think it's possible.
You
Yes?
said that the short high energy pulses were different for SDR SDR.
Uh-huh.
Why is that?
Because first of all, they need to be, it depends on your range, right? And so they need to be very short in time. That depends on your sample rate, how high your sample rate is. Then you need a few samples to generate your pulse, and so your sample rate is limited, and yeah, that's why. Yes?
What do you choose as frequency again?
Sorry?
What do you choose as frequency?
2.4 gigahertz,
Yeah, but why?
which is maybe not the best idea. Oh, why? Yeah.
Yeah.
Because
What
these
happened-
pens,
Uh-huh.
they're waveguides, and they are resonant at around that frequency. So it's pretty easy to tune them to 2.4.
But will you see something different if you use their frequencies? If you want to use their cans, different type of antennas. But will you see something different? What will you see different?
So what do you mean? I mean, the operation principle is the same, no matter what frequency you use. But, I mean, you need other antennas, and other antennas would be good because at 2.4 you get all this Wi-Fi crap disturbing your measurements. But
Broadcast.
broadcast, yeah, that's what you get. But I think I haven't gotten your question correctly.
Nothing. I was saying like it doesn't matter what frequency you use except for the antenna.
Yeah, I mean, you have different propagation, and you have different range, and yeah, of course that matters. Yeah, it does.
High frequency, wavelength.
Yeah, well, yeah, the resolution is better. Yeah, that's why you want it for that the wall penetrating stuff and the body scanners everybody's talking about. You want high, like 60 gigahertz or something like that. Somebody else.
What's the best brand of coffee?
Oh, I forgot. It definitely wasn't Starbucks coffee. I don't know. It's important, but I forgot. Sorry. All right. Yeah.
Thanks, Julian.
Thank you.
Thank you very much, Julian. So let's take 5. Is there any more pizza left? Any more beer? If there is, then please help yourself. We're just going to contact our remote speaker in Belgium, make sure he's ready to go. Last I heard, he was up and ready and just grabbing a bit of breakfast. So we'll check in with him and set that up. Jesus, do you have any luck setting up your demo again?
Wait.
Okay, so he might be back with that. So we'll just take a quick break and then resume with our final speaker, which should be really cool, a live demo of multi-PSK. So hang tight, we'll be back.
Detecting outputs very close together. With more resolution.
Yeah.
You can see that this really things are very
Pretty much.
together.
That's why it should always.
I don't know if these movement or things.
Well, it's tricky because if you want to penetrate something like sheetrock, you're going to want to be using lower frequencies, right? Once you get past about 3 gigs, cardboard and walls and stuff start becoming very, even 2.4.
Yeah, well, people often talk about terrorists.
What's going to get me?
It all depends on the material. If I were penetrating on sheetrock, I would want to use lower, hundreds of megahertz.
Well, the problem is you know,
If you're only trying to look at the side of the wall,
you're just trying to see what sort of height you want working on that covers your apartment.
yeah, and probably what you want to do is some sort of thing that's
Yeah, well, what do you think about that time? I feel like it's a single A scale. Just kind of holding
So just as a quick interlude, that demo that didn't quite work initially, hopefully will work now, so we're just going to have another look at it.
in that case, I would say a really nice directional antenna. This is a 2.4 Yagi? 2.0. Oh, log periodic.
I don't have, but they're good for broadband.
Oh, that's really cool.
Yeah. So
That's one that's called a unicorn.
and then you could, I guess, use your hacker rock. So one of these, you can stand across the wall. Because, you know, if you're putting on a 5-degree part of this
Yes.
Alright, so this is the augmented reality. So you see the map. I think it's it goes really slow because of the internet logos. So basically, you can see the map where we are right now. This is the mission. So if I have my backend here, you will see a lot of things showing. You know, the access points around, and then Bluetooth. And then when you raise this thing, you can see in real, like all the devices. I put some of the devices around, but again, because of the GPS resolution, you know, like there are some. So see, you will see these access points running around there, and in the next version, you can actually click on them and you can talk with them different ways. Again, it's difficult when it's indoors because of the resolution of the GPS. It's really low, you know, so it gets everything like this gets scattered around. But we have done that with Bluetooth devices, with Wi-Fi devices, and we're trying to do that with other devices as well. We're trying to, you know, hook up with some different radio. But you get the concept, right? You know, like you just can search for the devices that are around you and you know, talk with them by using the technology. With glasses, it will be easier. You just have to click something, you see a map, and then you look around, and then you will see what you see. So that's basically the demo.
Does it match that?
Right?
So it's crazy. This is excellent.
Yeah, that would be 50 ohms all across the entire 10-gig range. Yeah. Oh, wow.
Okay. So what's
That was a cool little demo. Glad you got that up and running. So now we're going to try setting up this live stream to Belgium. So just need 1 minute to do that.
As my friend is one of several.
what sort of equipment would you say is needed for, you know, high resolution distance? So bear in mind, this thing doesn't need to be far, maybe 18 inches or a foot is all it needs to be. So we're not doing super sensitive, powerful transmitters.
Say take control of your movement.
Yeah.
And so some sort of type of
Yeah, but what sort of electronics would you resolve close in space signals? You know, bear in mind that light travels in a nanosecond, a foot per nanosecond. So you're actually looking at in terms of things that separate like picoseconds or femtoseconds.
so you're also trying to get depth.
Yeah, depth information with high resolution.
That's something of meaning to know.
Maybe we try to
is quite like modulated. It's not just a continuous wave, but he was interesting enough. Continuous wave sonar is easy to prototype on your laptop. Just built in Argo, and then try modulating it and also.
Yeah, but what's the resolution?
Hopefully it works out.
Spaces. Maybe this.
Yeah, you have crazy high frequencies.
Well, anyway, I'd like to perhaps some unusual weird tricks like arrival times and phase, taking some phase.
Yes, it was off risk. I can't throw out a number, but it's like minus.
I mean,
And the number of schemes going
okay, so just
Actually,
Anyway, so I guess
That's great as that. We're having all the right brothers were hobbyists, right? It starts here. It just takes up experiments.
Actually,
I did not realize that Edis was actually in the Bay Area.
Yeah. That's part of what
All the cool companies I look at too. Yeah, it was pretty awesome. First new Gamma and oh yeah, first two was always a trap.
So you don't know what tricks they use up the sword.
Yeah, this like moving picture. Yeah, with this nice narrow. Across, and you also want something that, as it's sleeping, can differentiate and returns off of each other. So you probably have to modulate it.
That's 13 characters.
And you have to have a really high frequency to modulate it meaningfully. And you probably have to pay attention to the carrier phase as well.
Yeah.
So non-trivial.
I mean, do you have equipment that you can play with this time?
Can you hear me okay?
Yeah, I can.
Oh, we can hear you too, right? It's all working.
Alright.
Alright, so now we've got the Skype done, so let's do the Hangouts for your screen share.
Right.
I think that is going to be very levels. So it's an interesting map where we are in this position. So here, if I go back and here, let's say this sports around, and then previews, and then we create this red, like every devices. I put some of the
So you can share.
Got some Larson there. Is it? Are you able to turn off your microphone and cameras?
Yeah. Okay.
Yeah.
Okay, so can you still hear me through Skype?
Yeah, I hear you pretty straight.
Okay, I think we're pretty much ready to go when you are.
All right.
Is everyone good with this? Yep.
Okay, I can see you guys over there. It's quite dark, but I'm able to see you, so it's okay for me. I don't see what I'm projecting on the YouTube stream because it has too much lag, but I'm gonna just go forward with it and I'm just going to give it a go. Hello everybody, can you all hear me okay?
Yep.
Alright, well, good evening or good morning to the people that are looking at the broadcast stream in Belgium or in Europe. It's quite early here, so it's still dark. I hope you can see me okay with the lighting like this.
Yeah, it's great.
Okay.
Thanks for waking up.
I'm sorry?
Thanks for waking up nice and early for us.
No problem. Well, I'll introduce myself first. I'm Yves Cox. I live in Belgium. And it's Thursday morning here, 6 a.m. I think right now almost. So I'm quite happy to be the first remote speaker for you guys. Well, first the background about me. It all started 2 years ago when I got an RTL stick from a friend, and I became very interested in all about wireless communication. So it all went quick from then. Well, I got my full license from amateur radio operator, and I started learning a lot. It went fast on a fast day 2 years ago. So I now built my antennas, and I'm always listening on HF, VHF for new signals to detect and decode, just to learn about them. So I'm really interested in anything. Wireless or anything in the wireless spectrum. So that reason I also started my company together with a friend of mine. I'll slide it forward. Together with a friend of mine, who the guy who gave me the RTL stick in the first place. So we started Clear Sky Networks, doing spectrum analysis and Wi-Fi and free space opticals, so point-to-point links. So I basically made my job out of my hobby, so I like it a lot. Well, quick photo of my setup here. It's it's a Radio Shack in my porch actually. So a few antennas that I'm using and a point-to-point link that I made. So it's all quite fun to me. Next up, today we're going to talk about multi-PSK. Because I like multi-PSK because it's easy to use. It's a great tool just to decode stuff without knowing too much about the actual protocol or the actual modulation that's being used. And for that, I have my few tools. I have my HF. I have a Telat FDM Duo, which is a transceiver. Because I am a radio operator, I can use it as a transceiver too, but it's quite a good HF receiver too. So it's an SDR, direct sampling SDR, and it can go low from, I thought it was 40 kilohertz up to 52 megahertz. So it's quite wide banded, and it's the sensitivity is great. So it's a great tool for using the monitoring and listening I want to do. Also about the SDR is the 6 megahertz bandwidth in the maximum setting. So it's quite nice to have that wide of the HF to be monitoring that much, because it's not easy to find tools to have that much bandwidth in HF because of the complexity of the wavelength. Okay, next is my FunCube. FunCube is a really nice tool. It's also quite wide banded, from 150 kilohertz to 1.9 gigahertz. I use it a lot. It's a great tool. I use it with HD SDR. Great software. I think Bullet uses a lot also. So it's a great tool. And also the Atlas USRP D200, of course. Yeah, I like it a lot. It's I use it for recording and for extra wide data I want to monitor. So it's actually great also. And at last, the RTL stick. The RTL stick, best value for money I can buy, I think. So if any one of you guys don't have it yet, go and get it. It's ultra cheap, and you can do everything with it. Well, multi-PSK. Why multi-PSK? As I said, it has almost any mode I ever found on HF. So it's a great tool. Just decodes anything out of the box. Don't have to do anything about it. You just have to identify the signal and click on it, and it will decode it. So that's the easiest way to start learning about it, why it's being used, how it's being used, and I like it because of this. Well, it's not free, of course, but it's not that expensive, and it's made by a single guy, most of it, French guy, really nice guy. He's Patrick Lindendecker. He helps you if you email him about it. It's always, well, he's always able to help you, and it's just a great tool. He made it all by himself, so just buy it if you want to use it for real. And it's well, it's not throwing away money. Yeah, the GUI, it's intimidating to say at least. It's yeah, it's quite a steep learning curve, let's say. That's why we are doing the presentation today, to show you it's actually quite easy to use once you get used to it. Because, well, the GUI stays special, let's say, but workable. At a certain logic in it, so if you're using it, after a while, you'll get used to the GUI and you'll forget about the shortcomings of it. There is possibilities in multi-PSK there's possibilities in multi-PSK to do strings SDR reading of the FuckCube and the RTL stick, but I'm not a big fan of the implementation, so that's not the way I use it. I use a virtual audio cable. There are many virtual audio cables out there, but I use software called virtual audio cable. It's just called that. What's in the name? It's not freeware also, but it's quite good, and it has a lot of settings to it, so it's quite easy to use it, and it just works. So that's important too. Well, about the signal identification, I'm just going through this. About the signal identification, okay, I get a question here. Yeah, the virtual audio cable, I will show you later on what it's actually being used for. It's how can you say it? It's like a virtual plug from the output of your audio cards into your microphone inputs. So it's a sort of a patch cable, but virtually. So it's easy to use like this, to simply have an output of any program to the program. But I'll show you later on in the demo. Then you can see it actually in working. It's easier for me to show you than to explain what it's actually doing. So, okay, signal identification. Well, first thing we need to do is actually find a signal we want to seek, we want to identify, we want to get. So once you're set up and you're looking at your SDR screen and you found a signal. Well, the only thing I can say is record it, because many signals are sporadic only there, or yeah, just it's easier for you to record it and to analyze it later on than to have to be quick and always jumping around on the spectrum and tune in on other frequencies just to capture the correct frequency at the right time, because many of the signals have preambles and have headers that you have to capture, because otherwise the signal won't be decoded correctly. That's an important thing about multi-PSK. It needs the entire protocol, because it just needs it because it can be decoded otherwise. So record it. Every decent SDR tool has the capability to record the range you're viewing, the spectrum. So just you'll see it's a great tool. It's a great help in later on identifying the signal. For me, listening to a signal demodulated over AM, FM, or a single sideband is the best way, or not the best maybe, but a good way to identify the signal. Because after a while you get to know the certain types of modulation, you get to know the sound of phase modulation or frequency modulation, and you just get the sound of it, and that narrows down the identification process, and you'll get to find out lots faster what kind of signal. So, but that's requires, of course, that to have some experience and just saw the signal before, because yeah, you can't just know everything at once. So a big help in this is a web page, SIG-ID Wi-Fi, and it's well, it's a website. Maybe we can open it. Here it is, and it's a website. Can you all see it? It's a website that is, well, it has a lot of signals. It's like a reference page with all signals explaining what the signal is, where you can find it in frequency, and it has a footprint, a spectral footprint in it, and most of them also have demodulated audio capture. So it's easy to cross-check here, and maybe someone else found it before you and did all the research for you, so you don't have to check in yourself what it's all about, what the signal is actually used for. So other tools, of course, YouTube. Many people doing the same thing that I am, or what you guys are doing. So YouTube is a great tool too. And of course, Google Images and frequency lookup. Images can be used for a spectral image. If you find something that looks quite the same, or that looks like the signal you're seeing, you're in a good. It's a good start to identify it. So, in the frequency lookup, there's a lot of databases out there with all the frequencies and the signals that is being used on it. So, if you just look up the frequency you found, it's quite big chance you already find out what the signal is about. Today we're going to try and decode some signals, some stuff around there on HF and VHF. I'm not going to UHF signals because of first of all the lack in time, and most of the signals you can find that are quite interesting are on HF, some of them on VHF, but most of them on HF. And I really like HF because of the propagation properties. Of course, you can go quite many signal capturing that is broadcasted like thousands of miles away from you. So it's always interesting to see what's broadcasting on the other side of the world, I think. So there is one thing we are going to see today also. It's on VHF. It's the airplane ACARS system, VDL, and also some amateur modes, especially the SSTV one, broadcasted from the space station. So that's also on VHF. All right, I'll just open up my software here, my LR software, and start showing my setup. And we'll just start decoding, and I'll explain you going in the way when we're, how do I say it? I'll just show you multi-PSK while I'm decoding, and I'll just show you the setup. And if there's any questions, be free to stop me and ask them. Well, this is the software I'm using mainly for HF. It's a software from ELAT. It's only useful for ELAT, but you can also use HD SDR, or yeah, I don't know a lot of SDR Sharp, or there are a lot of tools out there that can be used. But I prefer this one because it's connected to my ELATs, and well, it's just good because I have multiple receivers, virtual receivers. So I have many receivers at once, and I can use it to port a single receiver to another software and do with it what I want. And so I'll show you how I use it. Well, first of all, we have to tune in on the signal. I'm already tuned in here at a HFDL signal. And HFDL is it's short for high frequency data link, and it's used by aircraft. So it's an information data link used for aircraft to communicate with the ground stations. And it's quite fun because they also send a lot of their current position and speed and all kind of data. They send over this link. It's short burst of data. It's over here. So it's a short burst of data, and there are two kinds of it. There is one in HF and there is one in VHF. In HF, it is single sideband modulated. And frequency shift keying over the SSB modulation. So the SSB modulation is just used to decode it actually. I'll open up my virtual receiver. This is too loud. Is the audio okay like this for you guys? The receiver, do you have anything?
Louder a little bit.
Wait, I'm going to try something else. Okay. How about this? Do you hear the signal?
Louder. A little bit louder. That's great.
Right, yeah, because I get a lot of feedback, so I don't, it's hard for me to actually get a sense of the audio level out there. Well, I'm just going to change this setup a little bit here. So what I'm going to show you now is the virtual audio cables I have set up here. Well, I have in my software it's possible to connect an audio cable to a virtual receiver. And as you see, I have 4 virtual receivers in the top. It's actually a demodulator I can put to any mode I want. And I can output the demodulated output. It's normally sent to a speaker. I can send it to a certain line. That's the virtual audio cable line. And it's actually a cable plugged in the computer, but virtually. So if I, let's say I want the virtual receiver 1, I want it to connect back to line 1. And later on in MultiPSK, I can use line 1 as an input. So it's a direct connection with my software for demodulated audio. And this way I get a lot more control over the frequency I'm using. I have a decent spectrum display like this. But while if I would be using the built-in MultiPSK SDR module, it's not just that good. It's just a frequency that is visible. The waterfall isn't that good and not that clear like this one. And it's much harder to detect signal. So that's the reason I use the virtual audio cable. Well, next thing I do is open MultiPSK. And well, this is the start screen of MultiPSK. It's quite intimidating to say the least, because of, it's a big mess. Actually, the main thing you need to set up is a sound card, and all the rest is extra setup that is needed for maybe other stuff, but not really necessary for a correct demodulation and correct decoding. So I want to set up the audio card interface. I'm going to set it up to line 1. So my input will be line 1, And that's the only thing I'm going to do for now. If you see here, there is the possibility to correctly or to directly connect a FunCube or Softwrap or RTL SDR. But as I said, I personally don't like the feature, and I'm not going to show it because of that reason, because it doesn't work that good. So the HD SDR or the LFSDR using a virtual audio cable will give you a lot more of it'll just work better because you have freedom in the software, a lot more possibilities in the SDR software. So next thing we do is go to the RxTX screen. It's called RxT because MultiPSK has the possibility to transmit also, but we're not going to use that because of today we're only going to demodulate stuff. So okay, I don't see any signal here, and that's probably because my volume is too low. So I pulled up my volume there. I put up my volume in the auxiliary audio a lot higher, so my MultiPSK gets the correct audio. I'll just enlarge it again. So if you see now, MultiPSK receives audio and it starts decoding right away. I haven't changed anything because it still was HDFDL selected. And as you see, a lot of information is passing by now. The only thing I needed to change was the audio level so that MultiPSK received enough demodulated audio, and this way, it simply decodes the messages it's receiving. So the fun thing about this is you can view it in text, you can view it like this and see what actual data is being transmitted, a little formatted in the way that it's readable, because otherwise it's quite difficult to read. But MultiPSK will format everything just the way so you can correctly see the data. If you want, you can turn on the data display to bits, and once the signal will be received, just wait a bit, you'll see it'll just show the different positions in bits. Not really useful for just simple decoding, but will be useful if you actually want to find out how the data is being sent out. I just can turn it back onto characters. Well, now MultiPSK has several handy tools on it. So it's able to show you the locations that are being sent out by the planes. I'm checking out if there's any airplanes being sent out there. I think one is being already. There's a little dot that's showed up here. That's an airplane that's this is live data, by the way. So this isn't recording, this is live data. So this is an airplane that is flying somewhere that has reported its position to a ground station in Bahrain. And every ground station has its own frequency. And apparently, I'm now connected to the ground station in Bahrain. If you want to find out about the frequencies, you can get a list of it by clicking on HFDL frequencies, and you'll just get a pop-up in Notepad that will show you all the frequencies. There could be more than this, but these are the most popular or the most current ones, I think. About HFDL, I think it's a quite recognizable signal. So if you see it, it's quite recognizable. If you see it in the waterfall, you immediately know that this is HFDL. So HFDL, I mean. So this way, it's easy for you to find new frequencies, or maybe airplanes transmitting on other frequencies, because there is a lot of aircrafts that are using this, and not only on the frequencies that are specialized for the ground stations for civil aircrafts. There's also the possibility to display it in Google Earth. If you click on Google Earth, it'll show you there, and it'll show you a pin where it received information. Just to zoom out a lot. So we just received something from Saudi Arabia. So it's fun. It's just fun to do with HDFDL like this because you get a lot about aircrafts thousands of miles away, and this way it's not like ADSB. ADSB is also fun, but it's limited to a range of 100 or 150 miles, I think, around you, depending on the tools you use. So yeah, that way HF communication is quite nice because I've happened to see some, if the propagation is right, you can see something on the other side of the world, an actual planes being reporting their speed, their ground speed and their position, and emergency messaging is also done sometimes over this line. So it could be quite interesting to just follow stuff on this link. Well, the same thing as you see here is also being used on VHF. I'm just going to minimize this one. It's being used on VHF. VHF is, of course, a whole other frequency range with its own properties. I'm just looking out for my. I'm just going to mute this audio now. There. Okay. So what I'm trying to do now is minimize my PowerPoint presentation. Okay. And I'm going to open up my HD SDR. And I'm already tuned in at the frequency that is being commonly used by VDL, so it's VHF data link instead of HF data link. I'll try and let you hear the signal. I'm just going to put the output again on line 2 because line 2 is the one I shared with the desktop screen sharing session. So normally you should be able to hear something. So it's quite a different sound. I'll turn it back off. It's quite a different sound. Okay. Because it's AM modulated, and of course the bandwidth is a lot higher, so they're able to burst a lot more data in a smaller time span. But actually, the rest of the data is quite the same. What I do now is go back to multi-PSK, and I only have to change the mode, and it'll. There, I have to click here where the data is, and after changing the mode, it'll try to demodulate the new data that is being received. Okay. It doesn't seem to be tuning in. Do you still hear the signal, or is the signal being forwarded to the correct port? I'm not sure right now.
We're hearing other things here.
Sir? Okay, hear it. Okay, I get a lot of audio feedback right now. Well, as you see, there's also the same data being transmitted, a little bit other formatted. But the nice thing about this is that the data we receive here is close by. So depending on your antenna situation, because of the VHF properties, it'll be more like a few hundred, over 100 or 200 kilometers away, or 150 miles. And this way, it's quite nice to find out what's actually near you. It also will report you about its airspeed or location and all cool stuff about it. So it's being used with the same properties, but then it will, like here, it's engine and APU data being sent here. So you see, it's quite nice to see some real data being sent from airplanes nearby. Being able to plot this on a local map or Google Earth. I'm going to use Google Earth because it's easier to zoom in. Let's see what we already received. So we received something over the channel here. So my location, just to get to see the range, my location would be here. Do you see my mouse pointer moving?
Yes.
Yeah, okay. So my location is here. You see the distance between these 2 points would be, I think, 200 or 200 to 300 kilometers away. So the range is quite okay. That's also because I'm using quite a large antenna for it. So it's quite mounted quite high. But this way you see airplanes quite nearby. And after a while, if you receive enough data, the aircrafts also report their ground speeds, their current location, and they will refresh all the data that is being sent constantly, because all the data that they send is like resent every few minutes. So if I display RX data again, Google Earth will refresh, and perhaps we have new data. Yeah, so new data already. There's a new pin here. So after a while, my whole screen will be full of pins, and even little aircraft. If it's sure it's an aircraft, it'll if we can identify the aircraft, then it will be actually shown up as a little aircraft. So it's nice to see that it will be modulated, decoded, and show you on a map what it actually received. Once again, this is live data, so I'm not really sure what is being received right now. I wanted to do it live because simply live data is a lot more cooler. Of course, I cannot change the results and all. You see the pilot talking here in AM also. So it's these airplanes are currently in the air right now and transmitting these data to me. Okay, just more data is being sent. So okay, let's move on to the next type of demodulation. I'll just close it for a minute. Yeah, it stopped where I left. Well, next thing we're going to do is a little bit more interesting, for perhaps because it's being used by NATO and military. No actual data is able to. You're not able to decode everything because it's encrypted, of course. But it's cool to just find out the way they try to communicate with each other over HF. It's still being used widely by many instances, many authorities, and it's just cool to see the headers and test messages being sent out. So because of it's a little bit more rare than airplanes flying across, I'm recording for this, and I'll show you the recording. I'm just going to stop this one, and I'll just show you a recording I made a few days ago. Starting up my SDR software again. And I'll show you this one. Let's find, I think this was the signal I wanted to let you hear. What is a USB? I'll let you hear it for a minute. It's quite a strange sound. It's this song about it you hear a lot of these signals. It's a digital sound. Is it audio like this? So you hear it. It's like an engine running or something. It's a special sound. You hear it a lot. I'm just going to turn it off, and I'll show you in multi-PSK what the data is being made. It's the STANAC 4285 mode, and this one is a test message, so it's okay to demodulate, it's okay to decode. And you see all the data is being sent out is a test message, just checking the connection and also keeping the frequency clear. We find a lot of these guys. This one is French, I think, because of all the I think it's French, some French instant authority that's keeping the frequency clear for their use. And there are times that you see the test message being stopped, and you see a lot of header information passing through about the receiver and the sender, and then everything is encrypted, so you're not able to see or hear anything about that type of signal. But well, you see something being decoded right here. Not all the time it's easy decoded like this, because STANAC 4285 is a mode that is not able to detect the byte rate itself. We have to do it by trial and error and find out the byte rate by changing the submode right here. Most of the time it's 600. If you're 600 bps, most of the time they use this. But there is occasions that you find that the higher byte rate is being used, and you just have to change it. Because if I do it right now, you'll see that the data isn't working, or it's like rubbish right now. So you know it's not the correct data unless it's encrypted. Because if it's encrypted, it could look like this, of course. But in this occasion, it's 600, and you see the test message being sent out. Actually, okay, here it is. So actually, there was a little bit of encrypted data there. So that's it for the STANAC modes. You'll find a lot of these in the HF region. If you want, you can try and find it yourself. It's full of it, so you can't miss it. As you see here, it's all STANAC. All the lines you see here is STANAC. So I just saw an interesting signal passing by here. I'm going to tune in on that one. I didn't know it was there, because the next one is ALE. We're going to see its automatic link establishment, and that's actually also a cool signal, because it's being used by today, and it's being used to open up a connection on the best used frequency available. So because of propagation properties, they're using this technique to find the best frequency to transmit data from one station to another one. And a lot of stations around the world are constantly monitoring these frequencies and waiting for a call being put out to them. So I'll just tune in on the data I just saw. I think it was around here. Okay, here it is. So if I'll just tune in, and I'll also tune in this receiver so you can hear it. And back forward. So you should be able to hear it in a minute or so. It's quite special sound here. It's a shift key here. Just put it again. And if you go look at it in multi-PSK, I'll just back it up again. If I go look at it at multi-PSK, I put it to ALE. Normally, I should be able to decode it. Because I haven't tried this one, just because it's popped up a minute ago, I just wanted to check it out. Well, there it is. Let's see if it's decoding anything. Because it may be possible I'm not tuned in correctly. Okay, I think I'm not tuned in the correct way. I'll tune in on this one. Let's try it again. I do have a recording though. I have a recording of ALE, but I want to try this one because I just saw it a minute ago popping up in my screen. So let's see if it can be decoded. And you'll just see a call sign popping up asking for another call sign. Okay, I don't think it's being able to decode it this way. No, let's just open up my other recording, which has ALE in it. It's this one. So it's also, what you see here is also HFDL, because I used it to record HFDL too. And I'm just gonna fast forward and find the signal I'm looking for. Here it is. And now I go back to multi-PSK. And here's the signal popping up. Voila, there it is. It demodulated it, it decoded it, and the actual data inside is a call sign, PLASPR. It's a call sign calling for another station, and I don't know for sure, but it's possible the other station isn't able to answer or hasn't heard this message because of propagation. That's all what link establishment is about. It's trying to call it on a certain frequency. If it doesn't get a response, it will try another frequency until it gets the station that it needs. So this way, all the correct data can be transmitted after the link has been established. Because after the link has been established, you will often hear voice unencrypted or perhaps encrypted, and also data being sent over the line, most of the time also encrypted, of course, because it's military. So it's normal. They don't show up everything they want you to know. I have some other marine modes. I'll go through this one fast. Well, the marine modes I have also recorded because it's a little bit more difficult to find the modes I'm looking for. But Navtex is one of them. Navtex is actually some kind of telex mode that will just transmit messages from ground station to ships, and from ships to ground stations, of course. It will be it'll be used for distress signals, but most of the time, mostly it's informational. So I think it was here, and I'll just put this one over so you could be able to hear it. I've set up multi-PSK, Navtex. Now I'll have to wait and see where the signal is appearing. It's quite difficult to find the signal. It is only a small burst, of course. I think it's best we just wait a bit. It's most of the time it's being used for. I see I'm tuned a little bit next to the signal. It should be tuned here. Most of the time it's being used for signals like cautions or. Okay, there is a signal. I missed it a minute ago. It's just there. and voila, there is a sync. And the nice thing about this is that multi-PSK tells you where to click on the right peak, so we just did. We clicked on the right peak and we see the synchro, it's synchronized, and it's starting to decode now. And this is constantly being streamed to vessels around the world. Every place has its own frequency, so the data you see is being sent out from, I think, Germany, because I see some German language over there. And all it's saying is some areas the ships need to caution, and some areas that it's not able to go, or because of work in progress, and all that kind of stuff. Another thing is the Global Marine Distress and Safety System. Also interesting because that's actually being used when ships are in emergency. And there's, let me show you. When there's a ship, when there's emergency going on the ship, they'll use this mode, and it will transmit all the data necessary for the Coast Guard or any other instance, so they can find the ship. And it's being transmitted on HF also, because this way propagation will make sure the ship will be found, because HF propagation will make sure the signal is being heard thousands of miles away. Okay, let's start the stream. And now I have to tune in another frequency, of course. Okay, I have a doorbell. And I click on GMDSS. I'll just wait for the signal appearing here, because this is actually short burst of data. Well, there it is. You see a preamble, and then there's the data being transmitted. And if we go look here, we see data appearing that is being demodulated. And this one is the coast station in Spain, apparently. And all ships called don't interfere. There's probably a safety caution or safety precaution that's being sent out to all the ships. It's possible to use this mode to send only to certain ships with a call sign, but this one is cool. Nice thing about it is it's sending identification data with it. You can use a button over here. I'm looking for it, web data, and this actually it'll open a link where you can find the ship that is that just transmitted, or the GO station that just transmitted these messages. This is a ground station. This isn't a ship, so I'm not sure. It probably won't find anything, but we can try it. And if I fill in this data, no, it doesn't find anything because it's a ground station. But the identifiers can be used on the internet to just find the ship, and you can find more information about it. And it's cool because you know it's real, and it's out there in the open, so it's just for grabbing. Another cool mode is WeatherFax. This is not the screen I needed. So WeatherFax is still being used, I think. I'm not sure because because of all the satellite links, it's a lot more easier to send it over there, but it's still being transmitted. So if I go and play this file, I'll show you WeatherFax. You'll hear its special sound. You'll immediately recognize it if you hear WeatherFax. It's also, there's a fun one. There's one right next to the Russian buzzer. Don't know if you in America can hear this one. You know this one because it's quite audible always here in Europe, and it's buzzing all the time like this, pulsing the sound, and it's quite a mystery signal, but nobody knows exactly what it's all about. It's a wiki page on it because, but still nobody knows what it is. But anyway, Here's the signal. So you hear it's pulsing, and each pulse is actually a line being demodulated or being sent out. I'll just mute the audio again. So if I tune in on this and go to multi-PSK, that's the weather fax being sent out there. I'll just click on fax here, click on the signal peak, and it'll start demodulated. And you see line per line, it'll start drawing image or try to draw an image. I haven't synchronized the signal now, because if you get the signal at the beginning of on the beginning of the signal there is a sort of preamble to it, which you use to synchronize the image. So it knows which one is the right side and the left side of the image. Now it's showing the left side in the middle or next to the middle. So I see the signal demodulated, that's good. Perhaps I can retune. No, it's okay like this. Now, it's not that good of a signal reception, I think, but you get the idea. There's a weather map in here that's being transmitted, and I can receive it like this. Normally, you're able to receive a better quality image, but this one is just bad reception, I think. But you see the idea. There's a weather image being transmitted, and I can receive it, and people on the ships can demodulate it. And they used to have printers connected directly to a receiver that will plot this line per line, so for real-time weather data and tidal data and all that stuff. So yeah, it's being received correctly. Just a little blurry because of the signal not being that great right now. Continuing, this is the last signal I wanted to show you on HF. There is a signal called DGPS, it's the differential GPS, and it's always transmitting with ultra high power transmitter. Just start the live data again. I'm going to try the live decoding, and I'll just tune in where it should be. I think around here. I'm going to zoom in a bit to see it a little better. Let's tune in. Here it is. So this is the signal I'm looking for. It's also some sort of frequency shift keying. You can see it in the footprint in the waterfall that it's shift keying constantly. I'll try to let you hear it. It's not that audible, so you hear it. It's a special kind of signal. But anyway, this is the signal. I'll show you in the DGPS. I'll show you in multi-PSK. Again, just click on the signal you want to decode, and it will decode it. This is the formatted data that's being sent out. So what this is for is actually fine-tuning the GPS receivers with fixed ground transmitters to calibrate the GPS receivers and use for ships for extra accuracy. So it's a lot of data being transmitted. There's another transmitter over here. I can click on this one, and there's other data because this one is Hoek from Holland and this is Oostende. This is actually my country being transmitted. And the transmitters are actually 50 kilowatt to 100 kilowatts or maybe more. So there's always some signal that you can find and try to demodulate. It's always there. So it's a very strong signal. Right. So you see, I can also basic display, which allows me to show actually the basic information about the signal without the background data, without the actual SAT IDs and the deviation factors. This will show you the signal is being demodulated, okay, and you can just see it working there. Okay, so the last one I wanted to show you was the recording I made this weekend, which is also quite nice. It's able to decode in multi-PSK, and the signal is actually sent from the International Space Station. They do this once in a while. They do this to celebrate stuff, to remember a certain event. And if I show you, I'll just fast forward it. It's actually SSTV, slow scan TV. And slow scan TV is actually a image mode that's being sent out. And it's being sent out by ISS on certain dates. It's not that often because we had the luck that last weekend they were transmitting, and I was able to capture some of the image. I'm just gonna find the signal where it starts. Here it is. It's the fun thing about receiving images from the International Space Station is that, well, simply it's not always there. So it's you have to make sure. Okay, just wait here. You have to make sure that the moment the ISS comes over, that you're decoding or that you're recording, because you only have a few minutes of recording time before it's past the horizon again, and you're not able to decode it again. So let's see if we're decoding right now. I'm just checking on the waterfall. It's SSTV. Oh, there it is. And it should start showing up some stuff, some data. I don't think that's correct. Well, I have to output it over here. Okay, that's the one you're hearing. Okay, let's try again. No, I think there's something off. Okay, I think I know why. I'm still, I was mixing my two receivers. I still had the other receiver in the range. Right. Isn't it receiving now? It's already a little bit weakened. Alright, let's see here. That's a problem with doing live stuff, of course. Not everything works perfectly. It seems to not lock on to the signal. It appears it's not locking on. I'll try another recording. Just a minute. I'll try this one. Here it is. This one is stronger. Of course, not every pass of the ISS I have to FM demodulate it. That's my fault. Okay, FM demodulation is important, of course. It's modulated over the area, so you have to use the correct demodulation to correctly visualize it, of course. Okay, I'll just put it here. And now the signal should be popping up any time now. I'm going to clear it. Synchronize, and it should be, there it is. Now we have an image. And it's just resynchronized. So now we see an image appearing also like the reflex line per line, and it's actually not like the way it's perfect. It should be. Let me check the GSER. Okay, we have to recalculate, of course, the Doppler shift because the ISS is passing over. You see it shifts in frequency because of the Doppler shift, and you have to retune it once in a while. Because it's FM, it's not that big of an issue, but you do have to retune it for correct demodulation. Otherwise, the image gets distorted like this. But you get the idea. So the image is being received. It's not in great quality, but I'm going to leave it here. So you just see it working like this. It does take a little bit more effort. So yeah. Okay. The image is being received. That's what you see now. Actually, that was it for me now. I just went past everything I wanted to show you. It's quite a lot, I know, I realized, but I just wanted to show you some cool modulations that being possible to demodulate on multi-PSK. If there's any questions, of course, it's always I'm always happy to help you. And there's a YouTube channel that is dedicated to multi-PSK, so you can find a lot of information over there. It's still being receiving here, so that's about it for me now. I hope you enjoyed it a little bit, and I hope you learned a little bit about multi-PSK and start using it. So I thank you for your time, and that's it.
Thank you. Considering how much live stuff you had there, it went very well.
Yeah, it's still dark in here, so I'm not sure. Okay. Well, yeah, this was my first time I ever presented something like this. I hope I wasn't too boring because I know it's difficult for me to realize how things. It's quite a dark image over there, so I'm not sure everybody was able to follow everything. But it was fun to do, and I hope to do it again anytime soon.
It was great. Thank you.
Yeah. Well, good night to you guys then.
Any questions
about
before
to start
we
now.
say goodnight?
Yeah.
Looks like everyone's happy. All right. Thank you very much, and a very good morning to you.
Yeah. Thank you. Good night. Bye-bye.
Bye.
Bye.
Right.
See ya. All right. Hello. Hello. Thank you very much for coming, both here and online. And thank you very much for everyone's help, particularly Neil, as always, and to our three speakers this evening. So catch you all next time in 3 weeks, I guess, down in the South Bay. Adios and good night.